Hey math kids, today we're going to talk about how to model periodic behavior, and we will just jump right in with an example. So it says the average daytime temperature for a city is given by this function. Okay, and that's measured in degrees Celsius, and T is the time in months after January. Okay, cool. So the first thing is they want us to sketch a graph of D from 0 to 24. And so we want to use stuff from like our previous videos to do that. So right here, we know the amplitude is 5. That means from the center point, it's going to be up 5 and down 5. This is going to tell us where our center point is, or our average. And so if we draw this on a graph, we're going to do like our middle right here at 20. And then up from there, we're going to go 5. So that'll be 25. We'll also go down from there by 5, which will be 15. Now, the only other thing we need to worry about is the pi6th. And the pi6th is going to help us find the period, but we have to do 2 pi, so, because that's the original period of cosine. And we divide that by the value that we see right here. And if we do that, it's like flipping this fraction upside down. So it's like going like this. So our pi's will cancel. 2 times 6 is 12. So our period is 12 months. And so going through the cosine function one time will take us 12 months. And we're supposed to graph it from 0 to 24. So we should go through 2 periods of cosine. Now this will look a little bit different than your book. Mapping these points in between is going to be a little helpful, but it's going to go. So the minimum is going to be right at 6, and the maximum at 12, minimum at 18, maximum at 24. Okay, so that's our function. That's part A. Now part B asks us, May is 4 months after January. Okay, so when T equals 4, find the average daytime. I was reading the answer part, sorry. Find the average daytime temperature during May. And so May is 4 months after January. I know that's a little weird because May is the 5th month, but the way that it's worded in the problem is 1 is 1 month after January. So we kind of start in February. So we go February, March, April, May. So we get 4, T equals 4 for that one. And so all we have to do is plug in T equals 4 right here. And so if we do that, we get 5 cosine pi6 times 4 plus 20. Okay, and then if we just plug all of that into a calculator, I feel confident that you can. Just make sure you're in radians when you do that. But if you plug it all in, you're going to get 17.5. Okay, and that is the degrees Celsius, is what that would be measured in. Okay, we have one more part. It says find the minimum average daytime temperature and the month in which it occurs. Well, we see we have a minimum here. We also see that we have a minimum here. Okay. So we could use T equals 6 or T equals 18, and we should get both of those. Now, the 6th month in the year, January, February, March, April, May, June, but remember everything's been shifted back one. And so it's going to be July. because July would be 7, but we're shifting it back 1. Just like when we were talking about t equals 4 is May, which is the 5th month, we're taking 1 away from that. So we actually need to go to the 7th month, come back 1, and that's where our minimum is, which is at 6, and so that happens in July. Okay? And that's it for that one. Now we're going to do another example. Okay, it says, on a hot summer day in Madrid, Anito pays careful attention to the temperature. The maximum of 41.8 degrees Celsius occurs at 3:30 p.m. The minimum was, this was the max. Okay, now the minimum was 27.5 degrees Celsius. Suggest a sine function to model the temperature for that day. Okay, so to find the median, like the mean, like the middle of our graph, where we do this thing with our sine function, we're just going to take that high and that low, add them together, and then divide by 2. So in other words, 41.8 plus 27.5, divide that by 2. So for this one, I think I'm going to pull my calculator open. Okay, so 41.8 plus 27.5, then we divide those by 2. We get 34.65. Since I got an exact answer, I'm not going to round to 3 significant figures. Okay, so the middle right here is 34.65. That's what we just found. Okay. Now, to find the amplitude, we want to know how much space changed from here to here, and then we just cut it in half, because really we only want the distance from here to here. Okay, so we're going to take the same two numbers. We're going to take 41.8, but we're going to subtract 27.5. That's going to tell us the total distance, but then we're going to divide that by 2, and so that will tell us just this piece of that distance. All right, so we're going to go 41.8 minus 27.5, and then we'll divide that by 2, and that tells us the amplitude is 7.15. Okay, so that's our amplitude. This is our mean. And then we also need to figure out the period, or the value that's going to go in our equation. So let me write out this equation again. So we have sine, and we have a b value right here. We have t minus c, and then we have plus d. So just to be clear, this is our a, and this is our d. Now, to find the b, we know that the original period of sine, which is 2 pi, divided by b is equal to 24, because we're talking about 1 day, so 24 hours. Now we want to solve that for b, so I'm going to multiply both sides by b. Let's cancel. 2 pi equals 24b. Divide by 24. Okay, and that's going to be our b value. So if we plug that into a calculator, or if we just simplify that, 2 and the 24 turn into 1 over 12, and so it's pi 12ths. Okay, so we have our B, we have our A, we have our D, so we just need to worry about the C. Now, so what we're going to do is we know that the maximum occurred at 3:30, and then we're going to assume that the temperature passed is about 6 hours, like to get to the minimum, and so we get 9:30 on that. And so AM, so we're going like 6 hours in the past. And then the day begins at midnight. So basically, we're going like 9.5 hours to the right. I know this is kind of confusing. And if you assumed like a slightly different time, that's okay. If you ended up doing 10 a.m. or 9 a.m. or something like that, but we're just kind of like estimating when that minimum value was. And there's not, even the book, they say they're confident that it was 6 hours. To be honest, though, I might assume that it's a little bit earlier. But whatever you assume it is, so even if we said like 6 a.m., we're going to shift it to the right 6. Whatever it is from midnight. So I'm going to stay consistent with the book, though, and I'm going to use 9:30 a.m. And so our C is going to be 9.5. And so if we write our final answer, we set this equal to y, we're going to say y is equal to our A value, and then sine, and then our B value, and then t minus our C value, and then plus our D value. So that thing in yellow is our final answer. Okay, I know that was kind of complicated. It's more about the conceptual understanding than anything else on that one. So if some of the details got away from you, don't worry too much. You can ask about that in MATLAB, and I can try to explain it a little bit better in person. We have one more example to go through in this. So the mean monthly maximum temperatures for Cape Town, South Africa are shown below. All right, so I think I'm going to have you just look in your book at this one, because maybe not. Maybe I'll write them out. So we got January, February, March, April, May, June, July, August, September, October. All right, let's zoom out. November, December. Feel free to fast forward the video to the part where I'm done writing this. 28, 27, 25.5, 22, 18.5, 16, 15, 16, 18, 21.5, 24, 26. Okay. Now this is just the month. This is the temp in degrees Celsius. Okay, and we're calling this time. All right. So it says we want to model the data with a trigonometric function of the form t equals a sine. This is just the same thing we used on the previous problem. Okay, and they're saying that January is congruent to 1, February is congruent to 2, etc. So it's not like the first problem on this video where it was off. This is going to make a little bit more sense, I think. So we want to draw a scatter diagram for the data. So when we do that, we're just going to say 1, 2, 3, up to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, representing the months. And then over here, I'm going to go just by tens, maybe. Okay, so we just plot this data. So at January, we were at 28. February, a tiny bit lower. March, a tiny bit lower. April, we're at about 22. May, we're under 20. July, we're even lower. June, we're even lower. And then August. And then September, it's almost symmetric. Should be. Alright, so it's not the best graph, but if my graphing ability was better, it would be roughly a cosine function, okay? Because we're starting high, we dip low, and go high, okay? Now, without using technology, they want us to estimate B, A, D, and C. So basically, they want us to come up with this equation. So our amplitude, I would say, or sorry, our middle, which is our D, is close to 20, but it's probably a little bit higher. So let's say 22 for D. Now the amplitude, so if that's 22, our lowest point is 15, so that's going to be a difference of 7. And so that's going to be 7. Okay, now our period is 12 months, so that we can actually like figure out. We can swap those, and so we get 2 pi 12ths, which is equal to B, and so pi 6th is our B. And then the last thing is C. How much have we been shifted over? I would say depending on which function we're using. Oh, we are using a sine. I didn't even recognize. I left that out in my brain. Okay, so we're using sine. So we actually need this part, the lowest part, sorry, right here. That needs to be shifted over. So that's 1, 2, 3, 4, 5, 6, 7. Interesting. And so I would shift that over. So I would say C is about 7. Okay. Oh wait, no, that's our low point. Sorry, I'm messing this up. So we need to look at our average and where that starts on our average, right here. Okay, that makes more sense. 1, 2, 3, 4, 5, 6, 7, 8, maybe 9. So I'm going to change that to a 9. But we actually want that to go to 0, so I'm going to make that a 10. So we want this point, because sine starts like this. Let me explain that a little bit better. It's like that. So we want this point to go here. So if we go 1, 2, 3, 4, 5, 6, 7, 8. Oh no, it's still 9. Take it back. Okay. So I would say 9. The book says 10, but their average was a little bit different than ours. And so that's just the way that we, it's a little bit off, but it should be fine. Okay. And then the last thing we need to do, we actually need to go to our calculator. And we need to enter it in. And I think I'm just going to show you on Desmos for now, because it's a little bit easier to see. So let's see. Desmos. Okay. And we want to enter a table. Let me get this so you can see it. So if you hit this plus sign, this comes up. We're going to enter a table of values. And so, once again, you can kind of fast forward this, but I'm just going to be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for the months. And then I'm just going to enter all of those. So 28, 27, 25.5, 22, 18.5, 16, 15, 16, 18, 21.5, 24, and 26. Okay. And we see there's our data. And then we can enter the equation that we created. Let's get rid of that. Bring it up here so I can actually type it in. Okay. So we're going to have y equals 7 sine of pi 6th x minus 9 plus 22. All right. So we look at that. We see it's a little bit off. I think the biggest place where we're off is this probably should have been 10. So if we change that 10 to a 9, we can see that it's pretty close. So that was our original, like that. And we're pretty close, so we feel pretty good about it. And we can even modify it as we're looking at it. Now, it's not perfect, obviously. There's other things we could do, like possibly our amplitude is a little too big, so we could do 6.5. That fits it a little bit better. Maybe even 6 is better than that. Maybe we shift it up too high, change that to a 21. Now maybe our amplitude needs to go back. So we could spend all day guessing and checking and even doing like half movements like that. Anyway, if you need additional help with this, come to Math Lab. Until then, calculator.